Hello there, and welcome to the Curious Mind Sleep Channel. I'm so glad you found your way here tonight. Maybe you've had a long day. You've had enough. Before we begin, I want to make you a promise. Every mystery we explore tonight has been verified by astronomers. From NASA's observatories, the Gaia mission, and peer-reviewed discoveries. No clickbait, no exaggeration, just truth that's already wondrous. Just the universe as it really is. And that's more than enough to spark wonder. You don't need to remember any of this. You can close your eyes anytime. Tonight, we're exploring why we still can't agree on what our own galaxy looks like. We live inside the Milky Way. We're embedded in its spiral arms, surrounded by hundreds of billions of stars. And yet, when scientists try to map our galaxy's true shape, they find mysteries that don't quite add up. Dark matter we can't see, structures we can't explain, a center we've never fully observed. For the next 90 minutes, we'll drift through the Milky Way's greatest unsolved puzzles, every fact verified, every mystery real. You're welcome to fall asleep whenever you'd like. If you're still here at the end, there's a final mystery waiting for you. But there's no pressure, no need to stay awake. Let your breathing slow. Let the world outside fade. Tonight, it's just you and the gentle mysteries of our cosmic home. Let's begin this gentle journey. Imagine trying to photograph your own face without a mirror. You'd see parts of yourself, your hands, your body, but your face would remain a mystery. That's our relationship with the Milky Way. We live inside it. Every star you've ever seen with your naked eye belongs to our galaxy, the cloudy band stretching across dark skies. That's us. That's home. And yet we don't know what shape it truly is. For decades, astronomers believed we lived in a spiral galaxy with 4 major arms, clean, symmetrical, elegant. Then better telescopes arrived, radio telescopes that could peer through cosmic dust, infrared observatories that revealed hidden structures, and the shape became less clear, not cleaner, more complex. The Gaia mission, launched by the European Space Agency, has mapped over 1 billion stars with unprecedented precision. 1 billion positions, 1 billion movements, 1 billion clues. And what Gaia revealed surprised everyone. Our galaxy isn't flat like we thought. It's warped. The disk of the Milky Way ripples and curves like a vinyl record left too long in the sun. Near the edges, the disk tilts upward on one side, downward on the other. Nobody fully understands why. Some scientists think it's the gravitational pull of our neighboring galaxies, the large Magellanic Cloud and the small Magellanic Cloud, 2 smaller galaxies orbiting us like moons. Their gravity might be tugging at the Milky Way's outer edges, creating these strange warps and waves. Others believe it's an ancient collision. Billions of years ago, a smaller galaxy might have crashed into the Milky Way. The impact could have sent ripples through the disk, like dropping a stone into still water. Those ripples might still be echoing today. But here's what's truly mysterious. The warp seems to be rotating. It's not static. It's spinning around the galaxy's center at a different rate than the stars themselves, as if the warp has its own life, its own rhythm, independent of the matter creating it. Scientists still debate how many spiral arms we actually have. Some say 2. Others argue for 4. A few claim there are dozens of smaller arm fragments. The Gaia data shows structures that don't fit any simple model. Spurs and branches and bridges between arms, chaotic beauty instead of elegant symmetry. Why does this matter? Because the shape of a galaxy tells us its history. The Milky Way's structure holds the story of every collision, every merger, every cosmic event that shaped our home over 13 billion years. But we can't read that story until we agree on what the pages look like. The center of our galaxy remains particularly mysterious. There, at the heart of everything, lies Sagittarius A star, a supermassive black hole 4 million times heavier than our sun. We know it's there because we can track stars orbiting something invisible. They whip around at incredible speeds, held by gravity we cannot see. But a vast curtain of dust stands between us and the truth. Thick clouds of gas and dust block our view. All the light from the center gets absorbed before reaching Earth. For decades, astronomers have tried to pierce this veil. We're like someone trying to see through a sandstorm. We know something massive lurks within, but its true nature remains hidden behind billions of tons of cosmic smoke. Radio telescopes can pierce through some of that curtain. They've revealed a complex structure at the center. Loops of energy, magnetic fields, shells of expanding gas, signs of ancient explosions. The black hole at the heart of our galaxy isn't quiet. It's active, it's violent, it's feeding. And yet, compared to other galaxies, our central black hole is remarkably calm. Some galaxies have cores so bright they outshine every star combined. Quasars, active galactic nuclei, places where black holes devour matter so voraciously they illuminate the cosmos. Sagittarius A star is almost quiet by comparison, almost sleeping. What happened to calm it down? Scientists think our black hole once fed more actively. Billions of years ago, it might have blazed like a quasar. Then the food supply ran low. Now it only occasionally snacks on a passing gas cloud or an unlucky star, but the evidence of its violent past remains etched in the structures around it. Even the number of stars in the Milky Way remains uncertain. Early Hipparcos satellite estimates suggested 100 billion stars. More recent observations push that number to 400 billion. The difference represents hundreds of billions of unknown suns, worlds we haven't counted, potential systems we don't know exist. Why such uncertainty? Because many stars are too dim to detect. Red dwarf stars, the most common type in the universe, barely glow. They're so faint that we can only spot the nearest ones. For every star we can see, there might be 10 we cannot. And then there are the stars hidden behind dust. The thick molecular clouds in the spiral arms block our view. Entire stellar nurseries remain invisible in optical light. Thousands of stars might be forming right now, just a few thousand light years away, and we wouldn't know unless we looked with infrared telescopes. The Milky Way's shape, its size, its mass, even the number of stars it contains, remain open questions. We live inside the very thing we're trying to understand. Every measurement is complicated by our position, every observation limited by our perspective. It's a reminder that the universe keeps its secrets close. Even here, in our own cosmic neighborhood, mysteries endure. And perhaps that's beautiful. Perhaps the not knowing invites us to keep looking, to keep wondering, to remain curious about the home we've never fully seen. Let that thought settle gently. We're explorers living inside the very territory we're mapping. And the map keeps changing, because the universe is not a fixed painting. It's a living, evolving story, and we're learning to read it one star at a time. Before we continue, let me tell you something remarkable about you. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now. None of these existed when the universe began. They were forged inside stars, created through nuclear fusion over millions of years, then released when those stars exploded. You are made of stardust, literally. Every atom in your body, heavier than hydrogen, was created in the heart of a dying star billions of years ago. You're not just observing the galaxy, you're made from it. You are the universe experiencing itself, a temporary pattern of star-forged atoms that has somehow become conscious enough to wonder about its own origins. Let that settle softly. You're connected to everything we're exploring tonight. Not metaphorically, physically, atomically. You are stardust that learned to think. Now, let's explore what holds all this stardust together. When you look up at a clear night sky, you see stars, thousands of them. But what you're really seeing is less than 1% of what's actually out there. The rest is hidden, invisible, made of something we cannot detect directly. We call it dark matter, and it makes up most of the Milky Way's mass. Here's how scientists discovered something they couldn't see. They watched how galaxies spin. According to the laws of physics, objects farther from a center should orbit more slowly. The planets in our solar system follow this rule. Mercury orbits quickly. Neptune takes forever. The farther out, the slower the motion. Galaxies should work the same way. Stars near the center should orbit quickly. Stars at the edge should orbit slowly. But that's not what astronomers observed. When they measured the speed of stars at the Milky Way's outer edge, those stars were moving just as fast as stars closer in, sometimes even faster. Strange to think of, isn't it? Unless there's more mass than we can see, mass that doesn't emit light, mass that doesn't interact with regular matter except through gravity, dark matter. An invisible scaffolding holding the galaxy together. Based on Planck satellite measurements, scientists estimate that about 85% of the Milky Way's total mass is dark matter. Only 15% is the normal matter we can see: stars, planets, gas, dust, us. Everything we've ever observed directly represents just a fraction of what's actually there. What is dark matter made of? Nobody knows. It's not made of atoms like you and me. It doesn't interact with light, so we can't see it, touch it, or detect it with conventional instruments. It only reveals itself through gravity. By the way it bends light from distant galaxies, by the way it holds galaxies together, by the way it shapes the universe on the largest scales. Here's the strangest part. Dark matter might be all around you right now. Billions of particles passing through your body every second. You'd never feel them, never know they were there. Invisible to every sense you have. Some theories suggest dark matter is made of particles we haven't discovered yet. Exotic particles with strange properties, WIMPs, some scientists call them. Weakly interacting massive particles. Despite decades of searching, no one has ever detected a WIMP directly. Detectors buried deep underground, shielded from cosmic rays, wait silently for a dark matter particle to collide with an atomic nucleus. So far, nothing. Other theories propose that dark matter might not be particles at all. Maybe our understanding of gravity is wrong. Maybe gravity behaves differently on galactic scales than we thought. Modified Newtonian dynamics, some call it. MOND. A few scientists think this could explain the galaxy rotation curves without requiring invisible matter. But most observations still favor dark matter's existence. The distribution of dark matter around the Milky Way remains mysterious. Computer simulations suggest it forms a giant halo, a spherical cloud extending far beyond the visible disk. Most of the galaxy's mass exists in this dark halo, invisible and silent, providing the gravitational glue that keeps everything together. But the exact shape of this halo, the precise density at different distances, whether it's smooth or clumpy, all still debated. Gaia's measurements of stellar positions might eventually help map dark matter's distribution by tracking how stars move through the invisible scaffold. But the work is slow, patient, because dark matter doesn't announce itself. It only whispers through its gravitational effects. Some scientists wonder if dark matter has its own stars, its own planets, maybe even its own life, a shadow universe existing alongside ours, forever out of reach. There's even speculation about dark matter interactions we don't understand. Maybe dark matter particles collide and annihilate each other, producing faint signals we haven't recognized. Maybe dark matter has its own forces, its own physics, entirely separate from the matter we know, a shadow physics existing alongside our own. The center of our galaxy presents particularly intriguing dark matter puzzles. Some observations suggest an excess of gamma rays coming from the galactic core, more gamma rays than expected from known sources. Could this be dark matter annihilation? Particles colliding at the galaxy's densest point? Or is it just ordinary astrophysics we don't fully understand? Nobody knows for certain. Dark matter also plays a role in galaxy formation. In the early universe, before stars existed, dark matter began clumping together under its own gravity. These clumps created gravitational wells. Normal matter, the gas and dust that would eventually form stars, fell into these wells. Galaxies formed where dark matter had already gathered. Without dark matter, galaxies as we know them couldn't exist. The gravity from normal matter alone isn't strong enough to hold a spinning galaxy together. Stars would fly apart. The Milky Way would unravel. We owe our existence to this invisible substance we've never directly touched. The search for dark matter continues. New detectors, new theories, new observations. Scientists look for signs in particle accelerators. They study the cosmic microwave background. They observe gravitational lensing around galaxy clusters. Every method provides another clue, but the picture remains incomplete. And yet, despite not knowing what it is, we're certain it's there. Like knowing someone's in a dark room not by seeing them, but by hearing them breathe. It's humbling, really. We live in a galaxy where most of the mass is invisible, where the majority of what holds our cosmic home together is something we don't understand, where the scaffolding of reality is made from a substance that exists in our equations, but not in our hands. And yet, this mystery doesn't diminish the beauty. Perhaps it enhances it. The universe is stranger than we imagined, deeper, more complex, full of layers we're only beginning to perceive. The darkness between stars isn't empty. It's alive with invisible matter, a cosmic web we cannot see but can feel through the orbits of stars, through the structure of galaxies, through the very shape of space itself. You're floating through a galaxy held together by something invisible, supported by forces beyond your perception. It's a reminder that reality is not just what we can see, it's what we can infer, what we can calculate, what we can glimpse through the shadows cast by things we'll never touch. Let that thought drift with you. You're held by invisible forces, just like the stars. Remember earlier when we talked about why we can't agree on the galaxy's shape? Here's something that makes it even stranger. The Gaia mission recently discovered something astronomers call stellar streams, long rivers of stars stretching across the sky. These aren't part of our galaxy originally. They're the remains of smaller galaxies the Milky Way has consumed. We're a cannibal galaxy. We grow by eating our neighbors. And those warps and structures we couldn't explain, many of them are scars from ancient collisions, remnants of galaxies that no longer exist. The Milky Way's shape is a history book written in consumed stars. So when we ask what shape is our galaxy, the answer keeps changing, because we're still digesting our last meal. And in 4 billion years, when we collide with Andromeda, someone else might ask the same question about an entirely new galaxy. It's a reminder that galaxies are not static. They're alive, growing, changing, consuming, and being consumed. The universe is not fixed. It's a story still being written. Let that thought settle as we continue our gentle journey deeper into the mysteries of stars. Stars are not permanent. They're born, they live, they die. And in the Milky Way, all three processes are happening right now. Deep within the spiral arms, hidden behind veils of gas and dust, stars are forming. Not one at a time. In clusters, dozens, sometimes hundreds of stars emerging from the same cloud. These are stellar nurseries, places where gravity pulls hydrogen together until it ignites in nuclear fusion. The process begins in molecular clouds, giant collections of gas and dust scattered throughout the galaxy. Some of these clouds are immense, hundreds of light years across, containing enough material to form thousands of stars. They drift through space, cold and dark, until something disturbs them. A supernova explosion nearby, the shock wave from a passing star, even the spiral arm's density wave compressing the cloud. Any of these can trigger collapse. Once collapse begins, gravity takes over. Dense regions pull in more material. The cloud fragments into smaller pieces. Each fragment becomes a potential star. At the center of each collapsing region, temperature rises, pressure builds, hydrogen atoms move faster and faster. Eventually, the core becomes so hot and dense that nuclear fusion ignites. Hydrogen fuses into helium. Energy pours outward. A star is born. But this process is hidden from our eyes. The thick dust surrounding newborn stars absorbs all visible light. For years, even centuries, a forming star remains invisible. Only infrared telescopes can peer through the dust and glimpse the stellar infants within. One of the most famous stellar nurseries is the Orion Nebula, about 1,300 light-years away, a region where hundreds of stars are forming right now. When you look at the middle star in Orion's sword, you're actually seeing a chaotic cloud of gas lit by newly formed stars. Some of those stars are only a few 100,000 years old, infants in cosmic terms. The Milky Way contains thousands of such regions. The Eagle Nebula's pillars of creation, the Carina Nebula's vast star-forming regions, the Rosette Nebula's sculpted gas clouds, each one a factory where stars emerge from darkness into light. But not all clouds are nurseries. Some are graveyards. When massive stars die, they explode. Supernovae. The explosion blasts the star's outer layers into space at speeds of thousands of kilometers per second. This ejected material forms an expanding shell, a supernova remnant, a cloud created by death instead of birth. The Crab Nebula is one such remnant. In the year 1054, Chinese astronomers recorded a bright new star appearing in the sky. So bright it was visible during daytime for 23 days. They called it a guest star. What they witnessed was a supernova, a massive star exploding 1,700 light-years away. Today, the Crab Nebula is an expanding cloud of gas and dust. At its center lies a pulsar, a rapidly spinning neutron star, the collapsed core of the original star. It rotates 30 times per second, emitting beams of radiation like a cosmic lighthouse. The remnant is still expanding, still carrying the energy of that ancient explosion outward into space. These death clouds serve a purpose. They enrich the galaxy with heavy elements. Everything heavier than helium was forged inside stars. Carbon, nitrogen, oxygen, iron, gold, all created through nuclear fusion in stellar cores, or in the explosive moments of a supernova. When a star dies and spreads its material into space, it seeds the next generation of stars with these elements. The molecular clouds that form new stars aren't pure hydrogen anymore. They contain traces of every element created by previous generations of stars. This is how the galaxy becomes richer over time, how complexity builds, how planets like Earth become possible. You are made of star remnants, the iron in your blood, the calcium in your bones, the oxygen you breathe, all forged in the cores of ancient stars that exploded billions of years ago. You're not just in the universe, you're made from it. Literally stardust given temporary form. Between birth clouds and death clouds, the galaxy is filled with more subtle structures. Planetary nebulae, not related to planets despite the name. These are shells of gas ejected by dying stars, not massive enough to explode as supernovae. Stars like our sun will eventually shed their outer layers, creating beautiful symmetrical clouds that glow for thousands of years before fading. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, each one a star's final artwork, a cosmic sculpture carved by stellar winds and radiation. At the center of each nebula sits a white dwarf, the exposed core of the original star, hot, dense, slowly cooling over billions of years. Dark nebulae exist too, clouds so dense they block all light from stars behind them. They appear as black patches against the Milky Way's bright band. The Coalsack Nebula, the Horsehead Nebula, silhouettes of dust that remind us not everything in space glows. Some things simply obscure. These clouds are not empty. They contain complex molecules, organic compounds, the building blocks of life. Astronomers have detected alcohol, sugar molecules, and amino acid precursors in interstellar clouds. The chemistry of life exists in the cold depths of space. Perhaps life's ingredients are more common than we imagined. The cycle continues. Stars form from clouds. Stars die and create new clouds. Those clouds form more stars. Each generation builds on the last. The Milky Way is not a static collection of stars. It's a living ecosystem. Birth, life, death, rebirth, over and over, for billions of years. And within this cycle, planets form, rocky worlds, gas giants, ice worlds, moons, asteroids, comets. The debris of star formations scattered into orbiting systems. Some planets might harbor life. Some might be dead. Some might be so strange we wouldn't recognize them as worlds at all. Every star you see could have planets. Most probably do. Recent discoveries suggest planets are the rule, not the exception. Billions of planets orbit billions of stars in the Milky Way. How many are habitable? How many actually harbor life? We don't know yet. But we know this: the galaxy is not a sterile place. It's chemically rich, diverse, full of the ingredients for complexity. The universe isn't trying to create life, but it's not preventing it either. The conditions exist, the materials exist, time exists. And in such a vast galaxy, rare things happen billions of times. You're part of this cycle, made from elements created in stars, living on a planet formed from the debris of stellar birth, breathing oxygen created by ancient life forms, using energy from our sun. Every breath connects you to cosmic history, every heartbeat powered by star-forged elements. Let that connection settle softly. You're not separate from the cosmos, you're woven into it, a brief pattern in the endless recycling of matter and energy. Temporary, beautiful, part of something much larger than yourself. Rest in that knowledge. You're home, in the deepest sense, made of the same stuff as stars, held by the same forces, part of the same ancient story. If you're still awake right now, you're part of something special. Most people have already drifted off, but you're still here, still curious, still listening. So here's a mystery just for you. Scientists have discovered something called the galactic habitable zone. Not all parts of the galaxy are safe for life. Too close to the center, and radiation from the black hole sterilizes planets. Too far out, and there aren't enough heavy elements to form rocky worlds. Earth sits in a perfect sweet spot, about 26,000 light years from the center, in a quiet region between spiral arms, far from supernovae, close enough to have heavy elements, remote enough to be safe. If the sun had formed anywhere else in the galaxy, you might not be here to wonder about it. The very fact that you exist to hear these words means our solar system won lucky in the galactic lottery. For those drifting off, that's okay. We'll keep exploring together. And for those still awake, thank you for staying curious. There's more mystery ahead on this gentle journey. When you see a picture of a spiral galaxy, the arms appear bright and distinct, elegant curves sweeping through space. But those arms aren't solid structures. They're not made of the same stars rotating together. The truth is stranger and more beautiful. Spiral arms are density waves. Think of them like traffic jams on a highway. Cars enter the jam, slow down, then exit on the other side. The jam itself doesn't move as fast as the cars. It's a wave of density moving through traffic. Spiral arms work the same way. Stars orbit the galactic center at different speeds. Stars closer to the center orbit faster. Stars farther out orbit slower. If spiral arms were made of the same stars staying together, the arms would wind up tighter and tighter over billions of years. Eventually, they'd wrap around the galaxy dozens of times. But we don't see that. Spiral arms stay loose and open. Instead, stars and gas clouds pass through the spiral arms as they orbit. When they enter an arm, they slow down slightly. Density increases. Gravity pulls materials closer together. This compression triggers star formation. New massive stars form and light up the arm with their brilliant blue light. Then, as stars exit the arm on the other side, the density decreases. The traffic clears. The spiral arms themselves rotate more slowly than the stars. They're like patterns rippling through the galaxy. Persistent waves of higher density moving through the disk. The stars come and go, but the arms remain. Nobody fully understands what maintains these density waves. Why do they persist? What keeps them from fading over time? Some theories suggest they're created by gravitational interactions with satellite galaxies. Others propose internal instabilities in the galactic disk. The math is complex, the observations incomplete, the mystery remains open. The Milky Way's spiral structure is particularly difficult to map because we're inside it. Imagine trying to understand the layout of a city while standing at street level. You can see nearby buildings, but the overall pattern, the shape of neighborhoods, the way streets connect, that requires an aerial view. We don't have that view of our own galaxy. Radio telescopes help. They detect emissions from hydrogen gas, which concentrates in spiral arms. By mapping hydrogen's distribution, astronomers piece together the arm structure. Infrared telescopes reveal old stars and dust lanes. Together, these observations suggest the Milky Way has 2 major spiral arms and several smaller arm segments, but different studies reach different conclusions. Some claim 4 arms, others insist on 2 major arms with many spurs. The debate continues because the data is messy. Observations from inside a spiral galaxy will always be ambiguous. What we do know is that spiral arms are sites of intense star formation. The density wave compresses gas clouds. Compression leads to collapse. Collapse leads to stars. Massive blue stars form in the arms and illuminate them. These stars live fast and die young. They explode as supernovae while still in the spiral arm. Their explosions trigger even more star formation, a cascade of stellar birth. This is why spiral arms appear blue in pictures. Blue light comes from hot, young, massive stars, the kind that form in compressed gas clouds. Meanwhile, the regions between spiral arms contain older, redder stars, stars that formed long ago and have drifted away from their birthplaces. Our solar system orbits the Milky Way at about 225 kilometers per second. It takes about 230 million years to complete one orbit around the galactic center. We call this period a galactic year. In the Sun's 4.6 billion year lifetime, it's made about 20 orbits, 20 galactic years. The Sun currently resides between 2 spiral arms, not in a major arm, but in a spur called the Orion Spur, a smaller branch connecting larger structures. We're in a relatively quiet neighborhood, not too much star formation nearby, not too many supernovae, a safe place for life to develop over billions of years. But Earth's position hasn't always been this calm. As the Sun orbits, it passes through spiral arms periodically. Some scientists speculate that transits through spiral arms might have biological consequences. More supernovae, more cosmic rays, potentially affecting Earth's climate or even triggering mass extinctions. Evidence for this remains circumstantial, but it's an intriguing possibility that our galactic environment might influence life's history. The spiral arms also affect the distribution of heavy elements. Stars form in the arms, live briefly, then explode. Their deaths spread heavy elements into the surrounding gas. This enriched gas then forms the next generation of stars. Over time, the galaxy becomes chemically more complex. The first stars contained only hydrogen and helium. Today's stars include every element on the periodic table. This chemical evolution makes planets like Earth possible. Rocky planets require silicon, iron, oxygen, and other heavy elements. These elements didn't exist in the early universe. They were created in stars and spread by supernovae. Only after several generations of stars had lived and died did planet formation become possible. You're living on a planet made from recycled star material, orbiting a star that itself contains remnants of previous stars. In a galactic neighborhood shaped by density waves, we're only beginning to understand. Every aspect of your existence is tied to processes playing out over cosmic scales and time scales. The density waves don't just affect stars. They shape the distribution of gas and dust. They influence where new stars form. They determine which regions are active and which are quiet. In a sense, they breathe life into the galaxy. Not biological life, but structural life, activity, dynamism, constant renewal. And yet, despite all this motion and activity, the overall pattern remains stable. The spiral arms persist. The density waves continue. The galaxy maintains its structure over billions of years. It's a balance between chaos and order, between randomness and pattern, between destruction and creation. Scientists use computer simulations to model galaxy evolution. They start with simple initial conditions, a rotating disk of gas and stars, and let physics take over. Gravity, pressure, rotation. Over simulated billions of years, spiral patterns emerge spontaneously. Sometimes two-armed, sometimes multi-armed. The patterns shift and change but never disappear. These simulations suggest spiral structure is a natural consequence of rotating disks. As long as gravity and rotation exist, density waves will form. They're not imposed from outside. They're emergent. A self-organizing pattern arising from simple rules acting on a grand scale. This is one of the universe's elegant principles. Complex patterns don't require complex causes. Simple forces, given time and space, create beauty and structure. The spiral arms of galaxies, the hexagonal clouds on Jupiter, the rings of Saturn, patterns emerging from physics, order from chaos. The Milky Way's spiral arms are not permanent features. They change over millions of years. Arms strengthen and weaken. New spurs form. Old ones fade. The galaxy is not frozen. It's evolving, slowly, on timescales that dwarf human history. But change is constant. In 1 billion years, the spiral arms will look different. In 10 billion years, the Milky Way itself will be different. It will merge with the Andromeda galaxy. The collision will scramble both galaxies' structures. Spiral arms will be destroyed. New patterns will form, perhaps an elliptical galaxy, perhaps something else. The future holds changes we can predict, but not prevent. But for now, the spiral arms turn. Stars pass through. Gas compresses. New stars ignite. The cycle continues, and you're here, briefly, observing from inside the structure itself. A pattern within patterns. Complexity within complexity. Let the spiral arms remind you that structure is temporary. Patterns come and go. Nothing is fixed except change itself. And yet, within that impermanence, beauty persists. Form emerges, life happens, consciousness arises, and contemplates its own cosmic context. You're part of that contemplation, a fleeting arrangement of star-forged atoms that has become aware of its own existence, asking questions about spiral arms and density waves, wondering about your place in the pattern, and perhaps that's enough. To wonder, to observe, to be briefly conscious in a universe that mostly is not. That's a kind of miracle, temporary, but real. Rest in that. You're a pattern in the spiral, and the spiral is beautiful. Last week, I asked our community a question. Sarah from Portland asked something beautiful. What Milky Way mystery keeps you up at night? The answers were fascinating. Over 300 of you responded. David from Tokyo wondered if dark matter has its own civilizations we'll never detect. Maria from Berlin asked whether consciousness could arise in neutron star magnetic fields. Questions so creative, they surprised even astronomers. For those still awake, here's this week's question. If you could ask the galaxy one thing and get a true answer, what would it be? Leave your thoughts in the comments. Next time, I'll feature my favorite responses and explore the science behind them. You're not just listeners, you're fellow explorers. Each question you ask makes this journey richer. Thank you for being part of this curious community, one sleepy soul at a time. Now from here, we move to one of the galaxy's most violent stories. The center of the Milky Way is not a peaceful place. Even though it appears calm now, evidence suggests a violent history. Explosions, jets of energy, waves of radiation sweeping through the galaxy. The core has been active, dramatic, perhaps even dangerous. Sagittarius A star, the supermassive black hole at our galaxy's center, sits relatively quiet today. It occasionally consumes a gas cloud or tears apart an unlucky star, but compared to the monster black holes in other galaxies, ours is calm, almost dormant. This wasn't always the case. About 6 million years ago, the galactic center experienced a massive energy release. Scientists call it the Fermi bubbles event. Two enormous bubbles of high-energy gamma rays extend above and below the galactic plane. Each bubble stretches about 25,000 light-years. Together, they span more than half the visible sky when viewed from Earth. These bubbles represent the aftermath of something violent. Perhaps the black hole consumed a large amount of matter all at once, or maybe two smaller black holes merged. The energy released was staggering. It carved out these vast structures in the gas surrounding the galaxy. The bubbles are still there today, still expanding, still glowing faintly in gamma rays. What triggered this event? We don't know precisely, but the evidence suggests periodic outbursts. The black hole feeds when material falls close enough. When there's nothing nearby to consume, it quiets down. Then, over millions of years, more gas accumulates. Another feeding event occurs. Another outburst. The cycle repeats. Even earlier in the galaxy's history, the center might have been far more active. In the first few billion years after the Milky Way formed, the black hole likely grew rapidly, consuming vast amounts of gas and dust, shining brightly as a quasar, outshining every star in the galaxy combined. Quasars are among the most luminous objects in the universe, powered by supermassive black holes actively feeding on surrounding matter. As matter spirals into the black hole, it heats up. Temperatures reach millions of degrees. Radiation pours outward. Jets of particles shoot from the poles at nearly the speed of light. Our galaxy's black hole could have been a quasar billions of years ago. If it was, life on Earth would have been impossible. The radiation would have sterilized any planets nearby. But over time, as the black hole consumed available matter, the quasar phase ended. The core dimmed. The galaxy settled into a quieter state. This raises an interesting question. Does galactic center activity affect life in the galaxy? Could outbursts from Sagittarius A star have influenced biological evolution on Earth? The answer is complicated. Earth sits about 26,000 light-years from the galactic center, far enough to be relatively safe, but not completely isolated. High-energy radiation from galactic center events could, in principle, reach Earth. Cosmic rays accelerated by the black hole might bombard our atmosphere, affecting climate, increasing mutation rates, possibly even causing mass extinctions. Some scientists have proposed that cosmic ray bursts from the galactic center could explain certain extinction events in Earth's history. The evidence is not strong, but the possibility remains intriguing. our cosmic environment is not static. We live in a dynamic galaxy. Events at the center ripple outward, perhaps even reaching our little planet. The magnetic fields near the galactic center are extraordinarily strong, thousands of times stronger than Earth's magnetic field. These fields channel plasma into loops and filaments. They accelerate particles to nearly the speed of light. They create structures visible in radio waves but invisible to our eyes. One such structure is the radio arc, a curved filament near the galactic center, about 100 light-years long, made of electrons spiraling along magnetic field lines. Nobody fully understands what created it or why it persists, but it's there, a monument to the magnetic complexity of the core. Stars near the galactic center orbit at incredible speeds. The star called S2 orbits Sagittarius A star every 16 years. At its closest approach, it reaches about 2% the speed of light. This is fast enough to test Einstein's general relativity in extreme conditions. Observations of S2's orbit confirmed that relativity accurately predicts motion near supermassive black holes. But S2 isn't alone. Dozens of stars orbit within a light-year of the black hole. They're packed so densely that collisions between stars might be common. When two stars collide, they merge, or one might be torn apart. The galactic center is a dangerous neighborhood for stars. Some stars near the center follow highly elliptical orbits. They plunge close to the black hole, then swing far out before returning. During their close approaches, they experience intense gravitational forces, tidal forces. The side facing the black hole feels stronger gravity than the far side. If a star gets too close, these tidal forces can rip it apart. We call this a tidal disruption event. Astronomers have observed tidal disruption events in other galaxies. A star wanders too close to a supermassive black hole. The black hole's gravity shreds the star. Gas from the disrupted star forms an accretion disk. The disk heats up and glows brightly. Over weeks or months, the glow fades as the material is consumed. Then the black hole returns to dormancy, waiting for the next victim. Has this happened at the center of the Milky Way? Probably, but we've never witnessed it directly. The thick dust obscuring the galactic center makes observations difficult. We might have missed disruption events simply because we couldn't see them through the curtain. The region immediately surrounding Sagittarius A star is called the central parsec. A parsec is about 3 light-years. This tiny region, by galactic standards, contains millions of stars. The density is so high that the average distance between stars is measured in light days instead of light years. In such a crowded environment, stars can be ejected. Gravitational interactions between multiple stars sometimes result in one star gaining enough speed to escape the galaxy entirely. These are called hypervelocity stars. They race through space at hundreds of kilometers per second, fleeing the galactic center, never to return. Hundreds of hypervelocity stars have been identified. Their trajectories, traced backward, point to the galactic center. Something there gave them the energy to escape, most likely close encounters with a supermassive black hole, or perhaps interactions in a dense star cluster near the black hole. Either way, they're exiles, cast out from the galaxy's heart. The galactic center also contains vast amounts of gas, molecular clouds, enough gas to form millions of stars, and yet star formation rates near the center are surprisingly low. Why? The strong magnetic fields might prevent gas from collapsing, or perhaps turbulence from black hole activity disrupts cloud collapse. The gas is there, the density is high, but stars aren't forming as rapidly as expected. This paradox highlights how much we still don't understand about the galactic center. It's a laboratory for extreme physics, strong gravity, intense magnetic fields, high densities, conditions we can't replicate on Earth. And yet, it's only 26,000 light years away. Close enough to study, too far to visit. The center of our galaxy is a place of extremes, where matter spirals into oblivion, where stars race at impossible speeds, where magnetic fields twist space itself. And yet, from Earth, it appears as just a bright region in the constellation Sagittarius, invisible to the naked eye behind clouds of dust, a hidden heart beating with violent energy. We're safe at our distance. The radiation from past outbursts has faded before reaching us. The magnetic storms remain contained near the core. The tidal forces that shred stars never touch our solar system. We observe from a safe harbor, watching the storm from afar. But we're connected to the center nonetheless. The black hole's gravity shapes the entire galaxy. Its mass anchors the orbits of billions of stars, including our sun. We circle the center like a moth around a distant flame, held by gravity, bound to the core even as we maintain our distance. Let that thought settle gently. You're orbiting a supermassive black hole. Right now, this moment, you're moving through space at hundreds of kilometers per second, circling the galaxy's heart, part of a grand cosmic dance that's been unfolding for billions of years, and you don't feel it, because motion is relative, because scale dwarfs perception, because the universe operates on levels beyond human sensation. But the motion is real, the orbit continues, the center pulls, and you're part of it. Rest in that knowledge. You're held by the galaxy, tethered to its core by invisible threads of gravity, safe, stable, part of something immense, something ancient, something beautiful in its violence and calm. Earlier, we talked about neutron stars. Remember those incredibly dense stellar remnants? Here's what happens when two of them meet. Sometimes in binary systems, two neutron stars spiral together. As they orbit, they lose energy to gravitational waves. The orbit decays. They get closer and closer, until finally they collide. The collision creates what scientists call a kilonova, an explosion so violent it forges heavy elements like gold and platinum. Most of the gold in the universe was born in these moments when dead stars kiss. In August 2017, scientists detected one of these collisions. For the first time ever, they saw the gravitational waves and the light simultaneously. Telescopes around the world turned to watch dead stars meeting in the darkness. You might be wearing the remnant of such a collision. That ring on your finger, those earrings. The gold formed when two neutron stars crashed together billions of years ago, then drifted through space, eventually incorporating into the cloud that became our solar system. You're wearing the memory of dead stars, a collision so violent it shook space-time itself, now quiet and golden on your hand. It's a reminder that even in death, stars create beauty. Even in violence, the universe forges treasures, and you carry those treasures with you. Not all stars end in spectacular explosions. Some fade quietly. Others leave behind objects so strange they challenge our understanding of physics. The Milky Way is scattered with stellar remnants, ghosts of stars that once burned bright. white dwarfs are the most common stellar remnants. When a star like our Sun exhausts its nuclear fuel, it swells into a red giant. Then, over thousands of years, it sheds its outer layers. The remaining core collapses into a white dwarf, about the size of Earth, but with the mass of the Sun. 1 teaspoon of white dwarf material would weigh about 15 tons. White dwarfs don't produce energy through fusion. They're hot only because of leftover thermal energy from their formation. Over billions of years, they cool and fade. Eventually, they become black dwarfs, cold, dark, invisible remnants. Though the universe might not be old enough yet for any black dwarfs to exist, even the oldest white dwarfs are still faintly glowing. The Milky Way contains billions of white dwarfs. Most are invisible to us, too dim to detect unless they're very close. But they're there, silent markers of stars that lived and died, each one a potential future for our own Sun. In about 5 billion years, the Sun will become a white dwarf. Earth will be gone. The inner planets consumed or destroyed. But the Sun's core will remain, cooling slowly in the darkness. Some white dwarfs exist in binary systems, 2 stars orbiting each other. If the white dwarf's companion is still a normal star, the white dwarf's gravity can pull material from the companion. Gas streams from the companion onto the white dwarf's surface. This gas contains hydrogen. When enough hydrogen accumulates, it ignites in a thermonuclear explosion. We call this a nova. Novae are not as powerful as supernova. They don't destroy the white dwarf. The explosion blasts accumulated gas into space. The white dwarf remains. Over time, it accumulates more gas from its companion. Another explosion occurs. The cycle repeats. Some novae recur every few decades. Regular reminders that even dead stars can violently erupt. But there's a limit to how much mass a white dwarf can accumulate. If it reaches about 1.4 times the Sun's mass, something catastrophic happens. The white dwarf can no longer support itself. Electron pressure, which normally holds up a white dwarf, fails. The white dwarf collapses, and in that collapse, carbon and oxygen in the core ignite all at once. A runaway thermonuclear explosion. The entire white dwarf detonates. This is a Type 1a supernova. Type 1a supernovae are important to astronomers. Because white dwarfs always detonate at the same mass, these explosions have remarkably consistent brightness. They're standard candles. By measuring how bright a Type 1a supernova appears, astronomers can calculate its distance. This technique revealed that the universe's expansion is accelerating, a discovery that earned a Nobel Prize and introduced the concept of dark energy. Even stranger than white dwarfs are neutron stars. When a massive star explodes as a supernova, its core can collapse into a neutron star. Imagine crushing the entire mass of the Sun into a sphere about 20 kilometers across. The density becomes so extreme that protons and electrons merge into neutrons. The star becomes one giant atomic nucleus. Neutron stars are the densest objects in the universe, aside from black holes. A teaspoon of neutron star material would weigh about 1 billion tons, more than all the cars on Earth combined. Gravity at the surface is so strong that falling 1 meter would accelerate you to thousands of kilometers per second. Neutron stars rotate, often very rapidly. Some spin hundreds of times per second. As they rotate, they emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we detect regular pulses. We call these pulsars, cosmic lighthouses, spinning remnants of dead stars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She detected regular radio pulses every 1.3 seconds. At first, she and her colleagues wondered if they detected alien signals. They jokingly called the source LGM-1, Little Green Men 1. But further observations revealed natural origins, a rapidly spinning neutron star. The discovery revolutionized astrophysics. Pulsars are extraordinarily precise clocks. The fastest known pulsar spins 716 times per second. Its period is so stable that it rivals atomic clocks in accuracy. By timing pulsar pulses, astronomers can detect subtle gravitational waves passing through space. Entire arrays of pulsars across the galaxy function as a giant gravitational wave detector. Neutron stars have intense magnetic fields, trillions of times stronger than Earth's. The magnetic field lines are so tightly packed they influence the structure of atoms. Matter behaves strangely in such fields. Atoms elongate into needle shapes. Chemical bonds break. New physics emerges. Physics we can't reproduce in laboratories. Some neutron stars have even stronger magnetic fields. Magnetars. Their magnetic fields are thousands of times stronger than typical neutron stars, so strong that they decay and release bursts of X-rays and gamma rays. Starquakes on the neutron star's surface trigger magnetic field rearrangements. These events release more energy in 1/10 of a second than the sun emits in 100,000 years. Only a few dozen magnetars are known in the Milky Way. They're rare, short-lived by astronomical standards. Their intense magnetic fields decay over thousands of years. Eventually, they become regular neutron stars. But while they're active, they're among the most energetic objects in the galaxy. In binary systems, neutron stars can spiral together. As they orbit, they lose energy to gravitational waves, ripples in space-time itself. The orbit decays. The neutron stars spiral closer. Eventually, they merge. The collision releases a burst of gravitational waves detectable across the universe. Beyond neutron stars lie black holes, regions where gravity is so strong that nothing, not even light, can escape. When the most massive stars die, their cores collapse beyond the neutron star limit. Gravity overwhelms all forces. The core continues collapsing. It becomes a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which nothing returns. Black holes are invisible. They emit no light. We detect them only by their effects on surrounding matter. Gas spiraling into a black hole heats up and glows brightly. Stars orbiting invisible companions reveal black hole locations. Gravitational waves from merging black holes announce their existence. But the black holes themselves remain dark, hidden by their own gravity. The Milky Way contains millions of stellar mass black holes, remnants of massive stars. Most are solitary, drifting through space, invisible and undetectable unless they happen to pass near something we can see. A few are in binary systems, pulling gas from companion stars, creating X-ray emissions we can detect. One such system is Cygnus X1. A bright blue star orbits an invisible companion every 5.6 days. The companion's mass is too high to be a neutron star. It must be a black hole, about 15 times the sun's mass. Matter from the blue star flows onto the black hole, heating to millions of degrees, emitting X-rays visible to space telescopes. Black holes don't suck in everything around them. Their gravity is strong, but only close to the event horizon. At large distances, a black hole's gravity is no different from any other object of the same mass. If the sun suddenly became a black hole, which it won't, Earth's orbit wouldn't change. The sun's mass would be the same, gravity would be the same. We'd simply orbit a dark, invisible sun instead of a bright one. The event horizon is the point of no return. Cross it, and you cannot come back. Time itself behaves strangely near a black hole. As you approach the event horizon, time dilates. From an outside observer's perspective, you'd appear to slow down, never quite reaching the horizon, frozen at the edge. But from your perspective, you'd cross in finite time, falling into unknowable darkness. What happens inside a black hole? Nobody knows. General relativity predicts a singularity at the center, but quantum physics suggests something else might occur. The two theories don't agree. Solving this requires a theory of quantum gravity, which we don't have yet. Black holes remain one of physics' deepest mysteries. Stephen Hawking showed that black holes aren't completely black. They emit radiation, Hawking radiation, caused by quantum effects at the event horizon. Pairs of particles spontaneously form near the horizon. One falls into the black hole, the other escapes. From outside, it looks like the black hole is glowing, very faintly. Over immense timescales, this radiation causes black holes to evaporate. But for stellar mass black holes, evaporation takes longer than the current age of the universe, far longer. By the time a black hole evaporates, every star will have died. Galaxies will have dispersed. The universe will be dark and cold. And still, black holes will persist, the last remnants of the stellar era. Eventually, they too will fade. But not for trillions upon trillions of years. The Milky Way's graveyard is vast. Billions of white dwarfs, millions of neutron stars, millions of black holes, each one a marker of a star's life, a monument to nuclear fusion, to gravity, to the life cycle of matter itself. You're surrounded by death, stellar death, but it's not morbid. It's part of the cycle. Stars die so new stars can form. Elements created in stellar cores seed the next generation. Death enables birth. Endings create beginnings. And in that cycle, you exist, made from remnants of exploded stars, living on a planet formed from stellar ashes, contemplating the deaths that made your life possible. It's a strange loop, life reflecting on the death that preceded it, consciousness emerging from the debris of dead stars. Let that settle, gently. You're here because stars died, because they spread their elements into space, because those elements gathered into new structures, into planets, into life, into you. You're a continuation of stellar death, a transformation of ending into beginning. And that's not tragic. That's the universe doing what it does, creating, destroying, creating again, over and over, forever. Rest in that knowledge. You're part of the cycle, held by forces that transcend your existence, connected to events billions of years old and billions of years in the future. A brief spark in the long cosmic story, but real, conscious, here, now. And that's enough. Beyond the bright disk of the Milky Way lies the halo, a spherical region extending hundreds of thousands of light years in all directions, mostly empty, mostly dark. But scattered within this halo are ancient stars, globular clusters, and mysteries about the galaxy's earliest history. Globular clusters are some of the oldest structures in the universe, dense spheres of stars. Each cluster contains hundreds of thousands or even millions of stars packed into a region only a few dozen light years across. The stars and globular clusters form together, all at once, over 12 billion years ago, when the universe was young. The Milky Way has about 150 globular clusters. They orbit the galaxy in highly elliptical paths, sometimes passing through the disk, sometimes far above or below it. Their orbits are not aligned with the galaxy's rotation. They're independent, ancient, like satellites orbiting a planet. The stars in globular clusters are metal poor. In astronomy, metals mean any element heavier than helium. The first stars in the universe contained only hydrogen and helium. No carbon, no oxygen, no iron. These elements didn't exist yet. They had to be created in stars, through fusion, through supernovae. Globular cluster stars contain very small amounts of heavy elements. This tells us they formed early, before many generations of stars had lived and died, before the galaxy was enriched with metals. They're relics of the Milky Way's youth. By studying globular clusters, astronomers learn about the galaxy's formation. The oldest clusters might have formed before the Milky Way itself fully assembled. Some could be remnants of smaller galaxies that merged to create our galaxy, captured during ancient collisions, now orbiting our galaxy as permanent reminders of those events. One of the closest globular clusters is Omega Centauri, about 16,000 light-years away. It's so bright you can see it with the naked eye from dark skies in the southern hemisphere. It looks like a fuzzy star, but through a telescope, it resolves into millions of individual stars, a dense sphere glowing with ancient light. Scientists think Omega Centauri might be the core of a small galaxy that the Milky Way consumed billions of years ago. Most of that galaxy was torn apart, absorbed into the Milky Way's disk, but the dense core survived. Now it's a globular cluster, a fossil of a long-dead galaxy. Other ancient stars exist in the halo outside globular clusters. Field stars, moving independently through the vast emptiness. These stars are also metal poor, also old. They follow strange orbits, sometimes retrograde, orbiting opposite to the galaxy's rotation. This suggests they formed elsewhere, perhaps in satellite galaxies later absorbed, or perhaps in the Milky Way's early chaotic days. One such star is He, 1523, Unwind. It's one of the oldest known stars, about 13.2 billion years old, nearly as old as the universe itself. It formed when the universe was only 500 million years old, before the Milky Way had taken its current shape. This star has witnessed almost the entire history of our galaxy. What was the universe like when He, 1523, 901 formed? There were no planets, no heavy elements. The cosmic microwave background, now cold and faint, was still glowing visibly. Galaxies were smaller, more numerous, colliding and merging more frequently. Star formation rates were higher. The universe was younger, more active, less structured. This star has survived unchanged for 13 billion years. It's a red giant now, slowly dying, shedding its outer layers. Eventually, it will become a white dwarf. But for billions of years, it was a main sequence star, quietly fusing hydrogen into helium, witnessing the galaxy's evolution from the outside. The halo also contains dark matter, lots of it. Most of the Milky Way's mass is in the dark matter halo, a vast, invisible cloud extending far beyond the visible stars. This dark matter provides the gravitational framework that holds the galaxy together. Without it, the galaxy would fly apart. The star's orbital speeds are too high for the visible mass alone to contain them. Scientists have tried to detect dark matter particles in the halo, experiments deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with an atomic nucleus. So far, nothing confirmed, but the search continues. If dark matter is made of particles, they're passing through the halo constantly, perhaps passing through you right now, invisible, undetected, ghost-like. The shape of the dark matter halo is uncertain. Computer simulations suggest it's not perfectly spherical. It might be slightly flattened or lumpy, with dense clumps and underdense voids. Observations of stellar streams, long trails of stars torn from globular clusters, might help map the dark matter distribution. These streams curve and stretch in response to gravitational forces, including forces from invisible dark matter. Stellar streams are beautiful and informative. When a globular cluster passes through the Milky Way's disk, tidal forces stretch it. Stars on the near side feel stronger gravity than stars on the far side. This difference pulls the cluster apart. Stars stream out in both directions, creating long, curved trails across the sky. One prominent stellar stream is the Sagittarius stream. It wraps around the entire galaxy, a river of stars torn from the Sagittarius dwarf elliptical galaxy. This small galaxy is currently merging with the Milky Way, being torn apart, its stars scattered into long streams. In billions of years, the Sagittarius dwarf will be completely absorbed. Its stars will blend into the Milky Way's halo, another galaxy consumed. The Milky Way is a cannibal. It grows by consuming smaller galaxies. The halo is full of evidence: stellar streams, orphaned globular clusters, stars with unusual orbits, all hints of past mergers. The galaxy wasn't built all at once. It assembled over billions of years, through countless collisions and absorptions. This process continues today. The Milky Way is currently absorbing several small satellite galaxies: the Sagittarius dwarf, the Canis Major dwarf, the Sculptor dwarf, each one being slowly torn apart, their stars added to our galaxy. This is how large galaxies like the Milky Way grow, by merging with smaller galaxies, by accumulating mass, by cannibalizing their neighbors. In about 4 billion years, the Milky Way will collide with the Andromeda galaxy. Andromeda is larger than the Milky Way, about twice as massive. The collision will be dramatic, not because stars will collide, they're too far apart for that, but because the galaxy's structures will be destroyed. Tidal forces will stretch both galaxies. Spiral arms will unwind. Stars will be flung into new orbits. Some stars might be ejected entirely, launched into intergalactic space. Eventually, the two galaxies will merge. Over billions of years, they'll settle into a new configuration, probably an elliptical galaxy, a smooth, featureless blob of stars. No more spiral structure, no more distinct disk, just a vast, elliptical swarm of stars. Scientists have nicknamed this future galaxy Milkomeda, or sometimes Milkdromeda, a blending of Milky Way and Andromeda. But that's billions of years away. For now, the Milky Way remains distinct, separate, slowly consuming its smaller neighbors, building its halo, adding stars, growing. The halo is a record of this growth. Every globular cluster, every stellar stream, every ancient metal-poor star, they're fossils, remnants of the galaxy's assembly. By studying them, astronomers reconstruct the Milky Way's history, piece by piece, merger by merger, and you're part of this story. The sun formed from gas enriched by previous generations of stars, stars that lived in the disk, not in the halo. You're not descended from the ancient halo stars. You're from a younger population. the disk population, born relatively recently in cosmic terms, but you're connected to the halo nonetheless. The dark matter halo holds the galaxy together, including the disk, including the sun, including Earth. You're held by the halo's gravity, supported by invisible matter you'll never touch, part of a structure far larger than the visible stars. Let that thought settle gently. You're held by forces beyond sight, beyond perception. You're part of a galaxy that extends far beyond what you can see. The visible stars are just the tip, the bright part, but most of the galaxy is dark, invisible, yet real. You're surrounded by darkness, but it's not empty darkness. It's full, structured, alive with invisible matter and ancient stars. The darkness holds you, supports you, keeps you in orbit around the galactic center. Rest in that knowledge. You're held, not by what you can see, but by what you can feel through mathematics, through observation, through inference. The universe is deeper than appearance suggests, and you're part of that depth. Nested within layers of invisible structure, held by gravity you cannot detect directly, part of a cosmic web you can only glimpse through shadows and effects. And that's okay. Not everything needs to be visible to be real. Not everything needs to be tangible to matter. You're part of something vast, something ancient, something beautiful. Even if most of it is darkness, nothing lasts forever, not even galaxies. The Milky Way, despite its grandeur, will change, evolve. Eventually, it will cease to exist in its current form. But the timeline for these changes stretches far beyond human comprehension. In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way. We know this because astronomers can measure Andromeda's motion. It's approaching us at about 110 kilometers per second, not toward the Milky Way's center, but at an angle. The collision will be a glancing blow at first. The two galaxies will pass through each other. Tidal forces will stretch both. Then gravity will pull them back together. They'll collide again and again, until finally, after billions of years and multiple passes, they merge into a single elliptical galaxy. What will this look like from Earth? Assuming Earth still exists, the night sky will change dramatically. Andromeda will grow larger. Over millions of years, it will swell from a faint fuzzy patch into a massive spiral visible across half the sky. Stars from both galaxies will fill the night. The familiar constellations will distort. New patterns will form. But individual stars will not collide. Space between stars is vast. Even in the dense cores of galaxies, stars are separated by trillions of kilometers. The galaxies will pass through each other like two clouds of smoke, interpenetrating, mixing, but mostly empty space passing through empty space. However, gas clouds will collide. When gas clouds from both galaxies meet, they'll compress, trigger new star formation. The collision will ignite a starburst, millions of new stars forming over a few 100 million years. The night sky will blaze with young, hot blue stars. Supernovae will occur more frequently. The galaxy will become a maelstrom of stellar birth and death. Eventually, the chaos will settle. The merged galaxy will contain all the stars from both the Milky Way and Andromeda, about 1 trillion stars total. They'll orbit in a new, less structured arrangement. The beautiful spiral arms will be gone, replaced by a smooth elliptical distribution. No more disk, no more clear rotation, just a vast swarm of stars in random orbits. The sun might be flung into a new orbit, or it might remain relatively unchanged. Computer simulations suggest about a 50% chance the sun will be ejected from the core into the galaxy's outer regions. But even if that happens, Earth's orbit around the sun won't change. The sun and its planets will remain bound together, just in a different part of the new galaxy. By the time this collision occurs, Earth might not be habitable anyway. The sun is slowly getting brighter. In about 1 billion years, the increased solar radiation will evaporate Earth's oceans. The planet will become too hot for life. By the time the galaxy merger happens, Earth could be a scorched, dead world. Unless, of course, humans or our descendants have migrated elsewhere. Looking further into the future, the sun will eventually die. In about 5 billion years, it will exhaust its hydrogen fuel. It will swell into a red giant, expanding until it engulfs Mercury, possibly Venus, maybe even Earth. The outer layers of the sun will be shed, creating a planetary nebula. The core will collapse into a white dwarf, and that will be the end. No more sunlight, no more solar system as we know it. Other stars will follow similar fates. One by one, the stars in the galaxy will die. Some as white dwarfs, some as neutron stars, some as black holes. Star formation will continue for a while, but eventually, the gas needed to form stars will run out, consumed by existing stars, locked in stellar remnants, dispersed by supernova explosions. In about 1 trillion years, the last stars will form. After that, no new stars. The galaxy will contain only remnants. White dwarfs, neutron stars, black holes, slowly cooling, fading. The universe will enter the degenerate era, an age dominated by stellar corpses. White dwarfs will cool over trillions of years, becoming black dwarfs, invisible, cold, still massive, but emitting no light. Neutron stars will cool as well, their rotation slowing, their magnetic fields decaying. Eventually, they'll become dark, silent spheres, detectable only by gravity. Black holes will persist longer than anything else. They don't cool like normal matter. They evaporate through Hawking radiation. But the process is extremely slow. A stellar mass black hole takes about 10 to the 68 years to evaporate. That's a 1 followed by 68 zeros. Incomprehensibly long, far longer than the current age of the universe. Eventually, even black holes will evaporate. And when they do, they'll leave behind only photons, particles of light, spreading through an ever-expanding universe. By then, the universe will be cold, dark, empty. Entropy will have maximized, structure will have dissolved. The era of galaxies, stars, and planets will be a distant memory, if anything remains to remember. But this is trillions upon trillions of years in the future. Right now, the universe is young. Galaxies are still forming stars, merging, creating new structures. We live in a vibrant era, a time when the universe is active, dynamic, full of light and life. You're living in the universe's middle age. The first stars have died, but many more will form. The cosmic story is far from over, and you're here to witness a moment in that story. A brief moment, but real. Now, if you're still awake, if you've made it this far, I have one final mystery for you, the ultimate mystery of the Milky Way. The question that encompasses all others. Why does the Milky Way exist at all? Why does anything exist instead of nothing? Why is there a universe? Why are there galaxies, stars, planets, life, consciousness? Why do you exist to contemplate these questions? Science can trace the history back to the Big Bang. 13.8 billion years ago, a singularity, an expansion, energy cooling into matter, atoms forming, stars igniting, galaxies assembling. But why the Big Bang? Why that initial state? Why those physical laws? Nobody knows. Perhaps there are infinite universes, each with different laws, most lifeless. But in a few, the laws happen to allow complexity, galaxies, stars, life. We exist in one of those rare universes, not because it was designed for us, but because only in such a universe could beings like us exist to ask the question. Or perhaps there's a deeper explanation we haven't discovered. A theory that unifies quantum mechanics and gravity, a principle that explains why the universe must exist, why these laws and not others. We don't have that theory yet, or perhaps the question itself is flawed. Perhaps existence doesn't need a reason. Perhaps it simply is. Brute fact. The universe exists because it does, and that's all there is to say. We don't know. And that's the final mystery, the deepest question, the one that might never be answered. But here's what we do know. The universe is here. The Milky Way is here. You are here. For a brief moment in cosmic time, conscious, aware, able to contemplate the vastness that surrounds you. That's remarkable. Against incredible odds, matter organized itself into you. Stars had to die. Planets had to form. Life had to emerge. Evolution had to unfold. And through that long, improbable chain of events, you arrived. Conscious, questioning, marveling at the mystery of existence itself. You or the universe become aware of itself, a pattern of matter and energy that has gained the ability to reflect on its own origins, to wonder about galaxies and black holes and dark matter, to ask why anything exists at all. And maybe that's enough. Maybe the fact of existence is more profound than any explanation could be. Maybe the mystery is the point, not to be solved, but to be experienced, felt, held gently in your awareness as you drift off to sleep. You're part of the mystery, not separate from it. You're woven into the fabric of the cosmos, made of stardust, held by gravity, carried through space at incredible speeds, part of a galaxy that's part of a universe that might be part of something even larger. You're nested within layers of mystery, and that's beautiful, because the not knowing invites wonder. It invites curiosity. It invites humility. It invites us to keep looking, keep questioning, keep marveling at how strange and beautiful existence is. So rest now. Let the mysteries settle around you like a blanket. You don't need to solve them. You don't need to understand them. You just need to be here, present, part of the cosmic unfolding. But if you find yourself awake later, if sleep hasn't come yet, there's another mystery waiting. What happens when two galaxies collide? When hundreds of billions of stars from the Milky Way meet hundreds of billions from Andromeda? It's not a distant future. It's already beginning. You can see the signs if you know where to look. The next time we explore together, we'll witness the collision, the chaos, the beauty of galaxies dancing in the darkness. For now, though, rest. The Milky Way will continue spinning. Stars will be born and die, galaxies will merge, the universe will expand, and through it all, the mystery will remain. Deep, profound, eternal. You're part of that mystery, a conscious moment in the long cosmic night. And that's a kind of miracle, temporary, but real. Know that you're held by the universe, supported by forces beyond comprehension, part of something vast and ancient and beautiful. You're stardust, and you're home. Sleep well and sweet dreams.